afternoon,
This
all.
conference will now be
Can you see
recorded.
my screen, Konstantin?
Yeah.
Okay, thank you. Good afternoon, all. As Konstantin already presented me, I'm Levente, and I'm a senior design engineer in Network Rail's Trackbed team. And Konstantin asked me last year about finding some suitable topic for one of these PWI presentations, and I agreed with my colleague at the time, Mohamed, to do something about geosynthetics. Unfortunately for us, he left the company, but he's still dealing with some synthetic materials that are being introduced in the trackbed. So he can still present you something, I hope, interesting in the second part of this presentation. So just to carry on with this. What are geosynthetics? Geosynthetics are synthetic layers and synthetic materials that we are introducing in the trackbed to enhance the properties or even replace entire granular trackbed layers. They include anything that starts with the geotextiles, robust or normal, geogrids, sand blanket replacement, geocomposites, geomembranes, geocells, and there is probably a long list that I cannot even mention now. So what we need to understand about these geosynthetics, we need to understand what they do before we specifying them. So they are only used in the right place, and they are achieving the goals that we are targeting. So in order to, another good question, do we need geosynthetics in the trackbed in the first place? From a technical perspective, in theory, probably not. In most of the cases, we have had granular materials. We have used granular materials for, I would say, almost centuries now, and they work very well. But unfortunately, in the real life, we do not have unlimited time or unlimited funding. So we need to reduce the amount of granular material that we are introducing in the trackbed. So this is when the geosynthetics are coming in very, very handily and nicely into this equation. So we are actually very, very lucky having them at our disposal as trackbed engineers. Okay, a trackbed engineer needs to understand very well what the functions are of the geosynthetics are. Otherwise, they will not be able to specify them in the right location. So I will just briefly mention some of the most important functions. These are not all of them, just the most important one. One of them is the separation function, as it is nicely presented in this sketch by Mr. Selig and Waters. They wrote a book which we consider the Bible of the trackbed. So what they say, and we are fully agreeing with that, the separation function is what it says on the tin, simply separates two materials. In our case, it's the coarse granular material on top, which is the new ballast, and other smaller sized particles at below, like the sand. So we are just separating them to avoid reducing the ballast life. Nice example of a photo. This is from one of my previous lives at Nuneaton, when I was a senior project engineer track. So that was a new SNC locations, and as you can see, a nice normal separator was installed on top of the sand blanket. Another function is the filtration. Apart from separating the two granular materials, we still want to allow the water to get through, because if we are trapping the water, that could lead to big problems and even create more problems that we ever had. And I will come back to that later. Another function is the transmission. This is in a way tying into the previous one with the filtration, but this one is about transmitting the water through the plane of the geosynthetics, not perpendicularly through it, is through the plane of the geosynthetic. You can imagine the geosynthetics are quite thin, so not too much water is expected to flow through the plane of that material. Another one, a very important one, but unfortunately for the bad reasons. So this is the isolation function, which is completely stopping anything coming through, even the water. And once the water is trapped under our trackbed layers, our geosynthetics, that is always leading to big problems, because that is creating high pore pressures, creating slurry, and eventually we are ending up with a very, very poor track performance. I will come back to that again later. So this is the later now. So as you can see from these photos, what we are seeing here are some impermeable membranes. And as I said, they are trapping water underneath, creating slurry and softening the entire trackbed. So we eventually are ending up with extremely poor track quality. And eventually all that layer, all that trackbed needs to be replaced with suitable material. From my personal experience, we are doing hundreds of trackbed investigations every year. Because we had installed the impermeable membranes for decades in the past, we are always coming across with impermeable membranes, and I can tell you in approximately almost 90% of the cases, they are associated with very, very, very poor track quality, very poor track performance. So we are recommending their entire full removal whenever possible. And unfortunately, again, they gave a very bad reputation for the geosynthetics in general. I wouldn't be surprised if any of you have heard in the past some track engineers, some track maintainer moaning about geosynthetics, which are creating problems on their patches. They are right, but they are only referring to these impermeable membranes. Another important function is the reinforcement and stabilization. Some examples: the geocells are providing a good reinforcement and stabilization function, and they are currently used to reduce granular material depths. Another material, which is another geosynthetic that is fulfilling this function, is the Geogrid. Multiple Geogrids can be used and act as the equivalent of geocells. So these are all very, very good geosynthetics that we are currently using to improve our track beds. A very legitimate question that can be asked, because we have seen in the past that geosynthetics have created problems. What can go wrong? And many things, but in general, I could split these in three categories. One of them is the actual design stage. So if we are specifying the wrong type of geosynthetics or a good geosynthetics in the wrong place, we could end up with poor track performance afterwards. Another one, geosynthetic procurement. We just recently had an instance when one of our external contractors wanted to procure a non-network rail approved geocell, and fortunately we found out and stopped that procurement process just in the last minute. The consequence would have been using a very bad substandard geocell that could have had even a safety implication, but definitely a financial one later on, because we would have to come back and replace that in entire layer with a suitable and network rail approved material. Most of the problems that we are finding are in the installation stage. So I can give you some examples in the next few slides. Throughout the years, I have personally issued many more or less formal guidances with regards to installation of geosynthetics. So on the right-hand side on top, that is one of my guidances that I issued to our colleagues in the track renewals departments. The Trackbed standard has got some parts dealing with geosynthetics. And on the left-hand side, you can see the title page of a geosynthetic installation guidance produced by our colleagues in technical services last year. And I had some humble input into that. And most of the examples in the next few slides are from that guidance. I will just give you some examples of good and bad practices in relation to installation of geosynthetics. For example, in terms of overlaps, when we have two consecutive rolls, obviously we need to overlap them. We are trying to keep that overlap to minimum, and we are advising on approximately 300 meters. Longer overlaps are to be avoided for several reasons. They are reducing permeability. You can imagine multiple layers of geosynthetics will be hard to penetrate by the water. In the case of the Geogrid, overlapping two geogrids means reducing the opening size of the grid, and that reduces the effect of the interlocking with the ballast. So there are various reasons for avoiding larger overlaps. One big one is the lateral overlap. In the last few years, we realized that there was something going on out on our renewal sites. Some geocell rods were cut in half, and for an easier installation, so I can understand their reason, for an easier installation, they were overlapping them in the center of the track, in the forefoot. However, this is not an acceptable practice for several reasons. Some of them I've just mentioned. Overlapping reduces the permeability, reduces the effectiveness of the grid because of the reduced opening size, and more importantly, when we are dealing with sand blanket replacement geocomposites, there is a high risk of slurry coming through that overlap. And also another possible negative impact on a renewal site, it's very easy to get some ballast particles trapped between the two overlapped rolls. And you can imagine our largest size is around 50-60 millimeters. That means that one of the geosynthetics, the top one, will be sticking out by around 50 millimeters, and that will be ripped out during a future renewal. Okay, some other implications are, again, the lateral overlaps. In case of multiple tracks or SNCs, obviously they are very wide, so we need to have some lateral overlap. But even in that case, we are trying to keep them to the minimum. So as you can see on those sketches, the larger overlap on the right-hand side, that is to be avoided, and just try to cut that geosynthetic to minimize that overlap. Oops, sorry. Another aspect to the geosynthetic installation is the cutting, the trimming on site, because there are various obstructions that need to be avoided. So we need to cut our geosynthetics to accommodate those shapes from the obstructions, and we need to do it in a safe manner to avoid hurting our staff. So we are always recommending the use of safe tools and safe methods of cutting geosynthetics. Some examples of possible bad practices that we have seen in the past. On the left-hand side, you can see a geosynthetic. This is a sand blanket replacement geocomposite combined with a grid lapped on the side. That's not good. So in this case, the width of the dig wasn't sufficient, and that lapping on the side, that will stop the water from the ballast layer coming out towards the cess. So it will be ponding for a long time in the ballast, and that will affect the performance of that ballast layer. On the right hand side, you can see a pneumatic tired vehicle. As some of you may know, the running of pneumatic tire vehicles is completely forbidden on any layers of the trackbed. They are creating all those indentations in the granular material. They are creating rotting, and they will prevent us from achieving a nice flat surface for these trackbed layers. Some other examples, you can see a very uneven surface of that geosynthetic, and the very likely consequence of that will be water possibly ponding in the ballast for a long time after installation, or even hitting all those peaks from of the geosynthetic during future renewal and ripping them out. That's the same photos, there's just a better angle. Again, another one where our colleagues from the side, they could have stretched those geosynthetics a little bit better to avoid all those creases and all of those geosynthetics, whatever they were, sticking out from the design level. Something else that we need to be very careful of is how to tie the geosynthetics into the line side drains, because if we don't do that well, we might unintentionally create some barriers between the trackbed and the drainage, and that will obviously stop the water getting where it should go in a proper drainage. Also, something else that we are not recommending, or actually we even banned on our network, wrapping geotextiles entirely around the drainage, because in time because there is a large amount of water taken from the trackbed towards the drain, they are likely to clog, so they could reduce the effectiveness of the drainage. Another good practice in relation to a geosynthetic, in the recent years, in the last around 10-12 years, we have installed micropiles on some of our tracks, but in very rare instances, some solid raft was installed on top to achieve a better transmission of the better transfer of the loading onto the pile and the surrounding soft material. So to achieve that, we are nowadays always recommending a solid layer, and the best one that we could find to date was a geocell layer that would achieve many things. For example, it will act as a good permeable layer, good filtrating layer, because we are recommending the sand as a fill in the geocell, and also it gives us a sufficiently solid hard layer that can transfer the loading properly onto the pile and onto the surrounding soft subgrade. We should always bear in mind we only recommend the piles in very bad circumstances, in very soft underlying conditions. So we are not recommending piles, not even geocells, everywhere. Okay, I think we need to go away from this presentation with that message. Wrong geosynthetics could have very severe consequences. So leaving aside the bad aesthetics from those two photos, what is important for us as track engineers is the performance of the track. And we know from experience, from painful experience, that wrong geosynthetics have created many problems on our network, but that's not because there was something necessarily wrong with the geosynthetic. It was about the people who recommended them and the people who installed them. So with the proper guidance, we can avoid that in the future, and we can avoid giving a bad name to some very good geosynthetics. Please take this table with a big pinch of salt. This was put together just to give an indicative volume of geosynthetics that we might be installing every year. So this is based on previous years, and They are just some estimated numbers, and I just wanted to show you that we are recommending very large amounts of geosynthetics on our track beds every year. So we are big fans of geosynthetics. I will let my colleague, my former colleague Mohamed, to take over and carry on with his side of the presentation, and we'll answer the questions later.
Thank you very much, Levente. I'll be sharing my slides in a second. Sorry about that. There we go. And I think is that clear? Can you see it?
I can see it.
Okay. Thank you very much, Levente, for the presentation. As usual, very interesting stuff about Trackbed. Well, to the people who don't know me, my name is Mohamed Wehbi. I've recently joined a company called GeoBear. I used to work as a senior Trackbed design engineer with Levente, and I've moved on to GeoBear to take the role of the technical director. So today I'll be talking to you about a new type of technology, a new type of geosynthetics, geosynthetic material. But before I start doing that, I thought, well, just to give a very brief introduction about who we are, really. GeoBear is a leading company when it comes to ground stabilization and settlement treatment. It was initially established in 1983 in Finland. Then in the late 80s, the UK business was started, and we've got more than 200,000 projects worldwide. GeoBear has an international outreach. We've got a number of branches worldwide in the US, Sweden, Finland, Poland, and China. And so from that sort of the variety, this kind of outreach, we tend to get a lot of interesting projects from all over the world. We do a lot of work in different sectors, in the highways, in the residential sector, and for airports, for energy and utilities. So we've been using this new technology, in all of these sectors, and we recently started to use it on the railways. So before I start getting into that, well, I thought, well, to try to kind of understand where we are really with geosynthetics. When we first started, when the railway was first invented, it was initially basically in the early 18th century. It was basically building railway tracks directly on soil. It's only until the early 19th century we started to realize, okay, we can actually do this better by introducing a ballast layer, which will better distribute the loads on the subgrade and get much better performance. And after that, the evolution started to accelerate at a rapid rate, and then we kind of started to understand the importance of membranes and geotextiles. Then we've got these very nice geogrids and geocells products, and we eventually ended up with almost a new type of geosynthetics, which like a composite structures that combines geotextiles with fibers. But since then, not a lot of innovations has been introduced to the world of geosynthetics. And today, basically, I'll be talking to you about a new type of geosynthetic that GeoBear have basically used. And how it can be used in the context of treating railway problems. So, just to give a very brief introduction to geopolymers. Geopolymers are expandable resins that can be injected into the ground at high pressure for the purpose of void filling and ground stabilization. So this is a video showing how the geopolymer looks like. So we basically inject it in a fluid state, and in a matter of seconds and minutes, it will expand and hardens. One of the most important properties of geopolymers, depending on the type of geopolymer, you can have different types of expansion or amount of expansion. So it can expand by almost up to 40 times its original volume. Now, depending on the application that we want to use the geopolymer with, we select the right type of geopolymer. So this is why it's quite important to understand this kind of characteristics, which will be kind of discuss later on in this presentation. Geopolymers have excellent engineering properties, so it has great compressive strength and tensile strength that can reach up to 7 MPa. So it can resist compression and it can resist tension at the same time. Like unlike conventional grouting, for example, or grouting type material, they're very good at compression but quite weak in tension. But here we've got like almost similar properties for both compression and tension. Another important property is the fact that depending on the type of geopolymer and how we install that geopolymer, we can actually have some sort of a control about what kind of stiffness the geopolymer would have. And this is quite important, especially when it comes to designing transitions, for example, or treating the trap bed in a specific way. You could actually control the stiffness to a certain degree to kind of give you the optimum design stiffness that you're after for your trap bed design. Also, and quite importantly, geopolymers have excellent properties to resist fatigue damage, so under cyclic loading. So if you take a piece of geopolymer and you basically cycle it for almost quite extensive amount of traffic, you would actually end up with very little amount of deformations on the long term. And if you actually compare the fatigue performance of normal geopolymers with what you have with excellent engineering fields like type 1, for example. Let's say you take the best type of type 1 you can actually find and cycle it and apply a loading cycles under that. It will probably, on the typical railway environment, it wouldn't last beyond 70 years. However, with geopolymers, if you apply the same loading conditions on a geopolymer, the geopolymer would at least last you for 120, 140 years easily with no problems. So that's a very important feature because that means you can actually put it underground, and actually this makes sense because we have been using this technology in highways, which has quite have a very similar loading environment to the railways. So, and there was no problems with it. So it basically that ties up very nicely with the finding of our testings. Other important features. For example, geopolymers can expand and rapidly harden and cure in a matter of a few minutes or seconds. It's a water-free solution, so we don't really require water to initiate the reaction. It's an environmentally friendly material, so the molecular structure of a geopolymer is very stable, so it's not going to contaminate the water or intermix with any other components. So it's very stable, it's not reactive. And it's quite light. It's a lightweight material, so if you compare the weight of a geopolymer to conventional grouting or concrete, for example, it will be 5 to 10 times lighter than those two materials. So it's a very light material, and it's not going to really add any extra dead load to your system or any of such compared to conventional grouting or other types of concrete. Now, moving on to some of the important applications. I mean, there's a very long list of possible applications how you can use it on the railways, but I thought I should pick up the most relevant ones to this presentation. And the first obvious application is the use of geopolymers to basically fill voids under slab tracks. Now, there's quite a when we design railway slab tracks, we always hope that it's going to last forever, but unfortunately, the ugly truth, it really never do. You're always going to get some sort of deterioration, and especially if you've got soft underlying conditions combined with poor drainage, you would end up eroding the subbase underneath the slab track, and as a result, you're going to end up cracking the slab, and that's what would happen. And when you get that, you're going to lose your track geometry very rapidly, you're going to get track faults, and so on and so forth. Well, what can we do about it? Well, we can actually identify the locations of these voids and drill to these voids via a 12 millimeter diameter hole, and start filling the geopolymer in these voids. As soon as the geopolymer get into the void, it will start expanding and filling at that void. Now, when you're actually also filling that void, when the void becomes completely filled, the slab track could actually starts to lift, and this is quite good because that can help us to restore the track geometry to the original design. So we can, as we were injecting, we can actually keep an eye on the levels of the slab and make sure that we actually get our construction tolerances to the millimeter. Another obvious application is the use of geopolymers to treat sinkholes. Sinkholes on the railways are quite rare. They're not that common in that sense, and but they sometimes they occur, especially near the seaside, and that could be because of the presence of dissolution features, the collapse of culverts, water leakage from pipes, or sea erosion. That could easily happen. And what you see here is a picture from Network Rail website, actually, for the Cumbrian Coast Railway line where a sinkhole actually occurred. What we can do with it, we can actually go in and identify the location of the sinkhole and start filling the cavity of the sinkhole with a geopolymer. The geopolymer will basically expand and fill the cavity in a matter of a few seconds or minutes, and it will harden right away. So you can run your railway line or your traffic right after that. The advantage of this compared to conventional grouting techniques, for example, you're not going to add water to the system really in that sense, because grouting will have some water content, quite large water content to it, and also it's lightweight and it will fill, and you're going to be using much less quantity because the geopolymer will actually expand. On another application, so far I've spoken about void filling applications, but also you can use the geopolymer to strengthen the subgrade, to actually make the subgrade stronger. Now, as Levente can actually tell you a lot about this, is that when we design a railway track bed, we always try to ensure that we've got sufficient thicknesses of the track bed layers to protect the subgrade and prevent deformations. Now, when we don't do that, for many reasons, that could be the case, and that's quite common on the railways, we end up with an under-design, and as a result, we don't achieve the desired track stiffnesses, and the track starts deteriorating. This is a video I've taken myself on one of the railway lines where there is a very soft underlying material on the track. And as you can see here, as the train passes by, if you keep an eye on the sleepers, you will see that the track is moving up and down, bouncing up and down quite excessively. So this is not that uncommon on the railways, and that could be due to a number of reasons, such as undetected soft spots, because we simply cannot survey and investigate every inch of the track. So there is a good possibility that you're going to be missing something. Budget constraints, sometimes as a lot of asset managers can actually testify for this, you simply don't have the budget to have a full-blown design. That's a fact of life. Or sometimes, and that's also quite common, is that the excavation, you've got excavation constraints. So you may have a nearby foundation and you can't really excavate that deep, or maybe a nearby slope, adjacent slope. So you can't really excavate that deep, and therefore you end up with an under-design. Well, what can we do about this? Well, we can actually inject the geopolymer directly into the subgrade. Now, when you've got clay subgrade, and you're injecting it at high pressure, the geopolymer at high pressure, what you would tend to do is you're going to fracture the soil. So when you're creating these sort of fracture, the fractures will almost create a path for the geopolymer to actually travel or penetrate through the soil, and almost create some sort of a root-like lenses into the substructure. You can see here, like it's almost like a root system that kind of spreads into the subgrade. And these roots will basically act like steel reinforcement in the reinforced concrete. So it's like a reinforcement, and these material, the geopolymer, has a much higher stiffness. So therefore, you're almost like adding a reinforcement to your subgrade without taking out the track or anything. You just basically go in and drill beneath the sleeper and inject the material without taking anything out. And these material will reinforce the subgrade and also add some confinement to the subgrade soil, and therefore you'll be able to reduce your deformations significantly. We've actually tested this. We've carried out some tests in Austria where we've had a testing pit, and that testing pit we filled it up with very soft soil that has a modulus of roughly about 4 MPa, and we've introduced our injections to that soil, specifically to injections. And what we did, we basically measured the stiffness before and after using an LWD. And this is what the results shows on the chart on the right hand side. Before the injections, we've measured in various locations, and we had an average value of stiffness of around 4 MPa. But after the injections, we managed to increase the soil modulus by almost a factor of 3 to almost 12. So that's quite an impressive increase in the stiffness of the soil just by doing the injections. And if you take these improvement percentages or improvement factors that you've witnessed in the test, we can actually easily apply that in a track renewal. For example, you've got a soft track, and that track that has this soft subgrade has a modulus value of 4 MPa. So the subgrade is quite soft. Now, if you go to the network rail standards, your design should be like 300 millibars plus 450 type 1. However, if you actually do the injection in this sort of configuration into the subgrade, you could actually reduce your design requirement from 450 to actually 150 type 1. So it's much shallower than what you would have had initially, because you simply strengthened the ground and your subgrade has a much higher modulus than what you initially started with. And this is all without really, you can really do it before the renewal happened, without, in weekend shifts or even midweek shifts. You can do it in stages. You can do targeting, for example. You can find your worst locations and do that discreetly. So there's a lot of options on how you can actually use this approach. Another technology we also have, we can use the geopolymer to create some sort of a pile-like structure. So we have these specially designed geotextile sacks that we can actually inject the geopolymer in, and these would actually fill, the geopolymer would start filling the geotextile sac and create a pile-like structure that has a diameter of almost 400 mil. So that's much wider than what you normally get from conventional micropiling. And as a result, we would basically get a much higher arching effect than what you normally get with conventional micropiling, and you get a much better load transfer. Now, obviously, this kind of solution is really reserved, as what Levente said initially, to extreme situations, like when you've got engineering peat or some really soft material that normal injections wouldn't be able to deal with. So that's a very interesting way of dealing with it. And it's all, again, you're not taking anything out of the track. You're doing the injections in a very non-disturbed way. This is how that pile structure looks like. We call it power piles, and this is how it's injected and expanded into the ground. We've actually carried out some testing in Finland to actually understand the carrying capacity of these piles, and we actually found out their carrying capacity exceeds 200 kilonewtons. Another type of solution that we can also do is the treatment of desiccated embankments on railway embankments. As a lot of you may know, our embankments have been built ages ago with poor compaction, inadequate drainage, and sometimes with poor vegetation management. Now, in many cases where you've got a special type of clay, a special type of fissured clay, you would, and you've got some large trees nearby, you would tend to get some sort of a swelling and shrinking action into the clay if the embankment is made of that type of clay. And as a result, what you tend to have is a low track deterioration in the wet season. And as we started to get into the dry season, the deterioration starts to accelerate and start decelerating again as we also get back to the wet season. So it's almost like a continuous shrink and swell cycle, and as a result, you will experience long-term deterioration. So that's quite a common problem on our railways. What we can do with this technology is we can actually inject the geopolymer in that fissured clay layer. And what we would do with that, basically inject very frequently, so inject a lot of injections, but small quantities of geopolymer. So we can actually fill all these fissures within the clay to kind of seal them off and stop the roots, the roots of the big trees nearby from sucking the moisture out. And what you would do with that, basically, you would end up with a situation where you kind of freeze the deterioration cycle, you intervene with the deterioration cycle. So instead of having a deterioration where you start with low deterioration, high in this dry season, then low again, you would almost freeze the deterioration cycle to something similar to what you would normally get from the wet season. We've done a lot of analytical modeling with this, and we've kind of got to the conclusion that we can actually reduce the embankment deterioration by almost 60%. And if you compare the cost of doing this sort of treatment as opposed to full reconstruction, you're almost reducing your cost by 40%. And this solution is we have been using this solution quite extensively in the residential building areas. So this is something that we've been doing for a while. It's not just, we haven't just invented this now. So it's something that we've actually done with residential buildings. Another application is the use of geopolymers to create transition zones. As some of you may know, if you've got a soft track that is transiting to a stiff track, like that is built, for example, on a bridge, you tend to create a transition zone, and that transition zone would basically experience high dynamic loading, ballast attritions, and differential settlement. And with time, it can cause some issues. So to mitigate this problem, we typically try to design some sort of a transition zone. But unfortunately, we don't really have a universally agreed standard or a method to create these transition zones. So in Network Rail, we never had a transition design, a bespoke transition design that we can use in our sites. You could actually find some good design suggestions in European standards, but all of these designs will basically involve massive reconstruction and deep excavations. And obviously, when you have a nearby, for example, bridge, the last thing you want to do is to dig deep and compromise the foundation. Okay. So what we can do with this? Well, we can actually inject the material. We can inject the material in such a way that we create transition zones. So we inject at different frequencies with different materials. So you kind of reinforce the subgrade stiffness gradually. So as you get to the bridge, you're almost smoothed out your transition. So that's a very effective way of doing it, and that would not involve any excavation or taking out the track or anything. So that's an in situ treatment to the problem. One final application where we can use this, where we can use geopolymer technology to create vibration barriers. So when you have a railway line near residential areas, you can actually introduce a vibration barrier using the geopolymer. So we almost install a thin geopolymer barrier that has a thickness between 2 to 5 centimeters in such a way that will stop the vibrations transmitting to nearby residents. And actually, some work has been done and testing has been done in Germany that shows the effect of having these very thin sheets and their effects on vibrations. And it was concluded that with these sheets, you can reduce ground ball vibrations by up to 60%. Now, the depth of that sheet is really dependent on the type of vibrations that we're getting and the frequencies, but it all can be really designed for and mitigated. So some case studies. Well, we've done some work on the railways. One of our most famous pieces of work we've done in the past. Well, we've done some work on Kentish Town slab track in 2016. So at that time, the slab track in Kentish Town was experiencing severe deterioration in track quality, and that was driven mainly due to soft underlying conditions and poor drainage. I should also note that this slab was built probably around in the 60s or 70s, so it's quite an old slab. And as a result of the dynamic action of the track and of the train, combined with the soft underlying conditions and poor drainage, the slab started to crack. What we've done, we've basically been commissioned to come out and carry out our injections underneath the slab to strengthen the ground and fill all the voids between the soil and the slab. And we've done that with what you see, with what we've got here as what we call here as the injection grid. So we had an injection interval of 1.5, so injected every 1.5 meter to kind of create the stabilization effect. And as we were injecting, we were actually carefully monitoring the slab level using laser levels to ensure that we raise the track to the desired geometry. Interestingly, is the maintainer that actually carried out some deflection measurements before and after the work has been carried out, and this is how the deflection looked like before the treatment. You can see significant deflections being observed at that location, reaching up to 6 millimeters. And after we came in and carried out our injection, you can see this is how the deflection would have actually looked like. That actually looked like after the injection, and we managed to reduce the deflection to 2 millimeters, so almost putting it right in the middle of the optimum range of track deflection. If you carry out some simple back calculations, you can actually see that we've managed to reduce track deflection by up to 70%, improve track stiffness by 167%, reduce rail bending by 26%, and reduced track vibrations by almost 50%. So it's quite a significant improvement. We've also looked at the track geometry before and after, so the track geometry from the measurement train before and after the treatment, and we looked at different geometry channels, twist, vertical fault, vertical top, right, and left, and dip angles. And the red lines, red curves represents the cases where we the measurements before the treatment, and the dashed box represents the area where we've actually done the treatment. So this is where we've got all our. This is how the track geometry response looked before applying the treatment. And in the next column here, where you've got the blue curves, these represents the measurements after or post the treatment, and you can see here what happened to the track geometry before and after. There's a significant improvement in track geometry, and we almost eliminated the dip angle and put back the track to the desired geometry. So that's also a very good indicator of its performance. Another case study, and that's the final case study here in this presentation, is a case study where we've done some work in Burma Road track slab track. That particular location is somewhere near Glasgow, somewhere in Glasgow, where there was about 150 mil dip in the track. So that's a massive dip, and you can see here it's quite visible from the picture here. The track was experiencing rapid deterioration, and as a result of this very poor track geometry, they had to introduce a 5 miles an hour speed restriction. The main drive for the deterioration was there was very poor drainage conditions underneath, and combined with loose uncompacted materials underneath the track, and basically that drove the deterioration. So what we've been commissioned to do at the time, where we were commissioned to actually lift the slab track to the desired position, also inject the material into that loose material, into the soft granular material underneath, and to strengthen its properties. And we were able to complete this work in two separate shifts over a single 24-hour possession. And then we've carried out some dynamic probing measurements before and after the treatment. And these are the different samples we had. So the blue lines represents the dynamic probing results before the treatment, and the red lines represents the dynamic probing results after the treatment. And you can see here, generally, we had an improvement between 50% to 100% improvement in the values of dynamic probing. So that would reflect in higher stiffness values of the substructure. And actually, this was not the final case study. This is actually the final case study. This is in Farnham Rail Depot. We had the depot there was experiencing significant differential settlement on the track, and as a result, you can see here, I mean, the picture just tells you how it looked like before we actually were commissioned to do any work. So had very poor geometry, and this was driven by poor compacted material underneath the slab and the depot. And we were commissioned to come in and carry out our injection, and you can see what's the after or post-treatment photo at the lower bottom right hand. You can see there's a significant improvement of the geometry. You can visibly see that. And that would conclude my presentation. Thank you all for listening. I hope you found that interesting. Please do not hesitate to ask us any questions. Thank you.